the Laplace equation. So the Laplace equation is this: del squared u equals 0 in some region, let's say omega in Rn, where this del squared u means the following. It is just the sum of second partial derivatives. So del squared u del xi squared. Yani ne demek bu? U sub x1 x1, u sub x2 x2, u sub xn xn. Okay, so that's called the Laplace equation. Okay. Basic concepts, and again we have maximum minimum principle. The maximum minimum principle. Okay, we will consider Laplace equation in regions in R2. So for us, u is a function from this open set, let's say, into real numbers, and by the del squared u, we will mean u sub xx plus u sub yy. Okay. All right. Şimdi burada bir takım fiziki şeyler var. Onlardan bahsetmeyeyim. Sonra yeri gelince bahsedeceğiz. Şeyden bahsedeyim. Types of boundary problems. Types of boundary value problems. This is known as, some kind of flow equation. It can be some electric charge or some liquid flow. Okay, so that's why it's very important in engineering. U may represent, usually it represents the flow of some object, usually also heat, of course, but liquid or electric charge, that kind of things. That's why it's important. Now, what is, for example, Dirichlet? One type is this Dirichlet boundary value problem. So in this case, the equation is the same, of course, this, let's say, but we have this condition on the boundary here in the region. So let's say you have some region in R2, okay? Inside this region, you have this equation. So at an interior point, this sum of second derivatives is 0. This means it's an harmonic equation, a harmonic function, right? If an equation satisfies this condition, it's called harmonic function. So it's a harmonic function. And what is that? It is actually the real part of an complex function, complex analytic function. But on the boundary, we have such a condition. At a boundary point, xy, you want your function to satisfy this condition. Okay, this kind of problem is called Dirichlet type boundary value problem. Newman type is this. Newman type boundary value problem. Okay. So we have again the same equation, but this time you have this. For xy in the boundary. Here, what is this? So here is our region. At a boundary point xy, I have so-called normal vector. So this is del n, normal vector. And this tells us that the derivative of u in this direction, so you have directional derivative in the outward normal, let's say, that derivative is equal to this gadget. Okay? Here there is no derivative, just the values of u is equal to this f, but here you have derivative of u at boundary points should be given like this. Tamam mı? Buna Newman type deniyor. Peki Robbins type boundary value problem. Burada da we have this del u del n plus c times u minus g is equal to 0. We have a mixed condition. Derivative plus the value of g u has to satisfy, a condition like this. So it's a combination of the two. Okay. This is called Robbins boundary value problem. Okay, then we have again, as usual, some theorems. The maximum minimum principle here is the theorem. So this is the maximum minimum principle theorem for Laplace equation. Let u xy be a 2 times differentiable, continuously differentiable function, so that inside it is 2 times differentiable and on the closure it is continuous. So this means what? At interior points it is twice differentiable with continuous second order partial derivatives. At the boundary points, it is only continuous. We don't ask differentiability on the boundaries. It is enough just to be continuous. So let this be a solution of Laplace equation. Namely del squared u xy, which is u sub x minus plus u sub y equals 0 in a bounded region omega with boundary del omega, then the maximum and minimum values of u xy are attained since it's a continuous function on a closed and bounded region, on a compact region. It has both maximum and minimum. And the conclusion of the theorem is that those maximum and minimum values should be attained at interior points. On the boundary of this region. Yani maksimum değeri her neyse o değere boundary'de ulaşıyor. Bu şu demek değil tabii ki. Hani içeride de aynı değeri alabilir ama içeride aldığı maksimum değeri boundary'de de alıyor. Yani şu aslında that is maximum of u xy on the closure is the same as maximum on the boundary u xy, and minimum on the closure u xy on this closed set, closed and bounded set, is the same as minimum on the boundary. Tamam mı? Dolayısıyla maksimum ve minimum bulmak için sadece boundary'lere bakmak yeterli. Aslında bunu you have seen this probably in complex calculus, right? Norm of an analytic function attains its maximum on a boundary point. So real part and imaginary part of an analytic function are harmonic functions. That's why we have this. Yine de şöyle yapalım bunu. Proof şimdi diyelim ki okay, şimdi since u is continuous, değil mi? Assumption gereği continuous on the compact closed and bounded set, compact set, u closure, it has a maximum value attained at some point say x0 y0. Biz ne göstermek istiyoruz? Bu nokta boundary'de olmalı. Eğer fonksiyon şey değilse, constant değilse tabii. Constant ise o zaman okey. Şunu iddia ediyorum. If u is not constant, o zaman tabii ki her noktada aynı değeri aldığı için, değil mi? Maksimumu her noktada almış oluyor. Then bu x0 y0 noktası boundary'de olmalı. Bunun ispatını yapalım. Proof of the claim. Assume on the contrary that this x0 y0 is not on the boundary and hence x0 y0 is inside the region. So in this open set, yani şu bizim omega'mız, daha doğrusu omega'nın closure'ı, bu boundary'si, değil mi? Diyelim ki böyle bir içerideki noktada bu maksimum değeri aldı. O zaman çelişki çıkacağını iddia ediyoruz. Okay. Yani aslında evet, şöyle diyeyim, aslında dur. İddia ettiğim şey şu olsun. Evet. İfadeyi biraz değiştirsem mi diye düşündüm de kitaptaki biraz farklı. Efendim? On the compact. Yani closed and bounded. Onu gördünüz değil mi? Kompakt kümelerde. Aha. Şunu ifadeyi değiştirsem mi diye düşündüm de. Şöyle şunu, yani notlardakine uygun hale getireyim de şöyle diyeyim. Okay. Okay. Assume that this value ux0 y0, the maximum value, is larger than m b boundary, which is just the maximum of u on the boundary. Tamam, bunu kabul edelim. O zaman okay. Şimdi şu var. Consider the function. Ben neye ulaşacağım? We will arrive at a contradiction, right? Aim arrive at a contradiction. Peki, bunu şöyle yapalım. Şuradan devam edeyim. Consider the function vxy, which is just uxy plus epsilon x minus x0 squared plus y minus y0 squared. Then for any epsilon positive vx0 y0, bu fonksiyonda x0 y0'yu koyarsak ux0 y0'yu buluyoruz. Because this is 0 at that point. And moreover maximum value of boundary on the boundary of the region of vxy nedir? Şundan küçük olacak. Bunun maksimum değeri boundary'de, pardon, u'nun bu fonksiyonun boundary'deki maksimumuna bakacağım. The maximum value of this function at the boundary will be less than the maximum value of this function on the boundary, which is mb, plus the maximum value of this function on the boundary. What is the maximum value of this function on the boundary? It is epsilon times the distance of x0, y0 to the boundary of the region, sorry, of this point to the boundary, which is less than or equal to d, where d is the diameter of this region. Yani şu resim çizersek şöyle, değil mi? This is omega. I am at this point. Bu nedir? At any point xy here. You look at this distance, right? It is just square of this distance. Bu neden küçüktür? Buradaki en uzun mesafe. Değil mi? So this is always less than the maximum of the distance between 2 points in this region. And that's what we call the diameter. In this case, I guess diameter is something like this, right? So these are like, the farthest away points. So this diameter is something like this. So this diameter, and this distance, which is this, is less than the diameter. So this is the what? Maximum. Since the region is compact, I can say maximum of what? Maximum of x minus x0, ya da şöyle diyeyim, x1 minus x2 squared plus y1 minus y2 squared. Nedir bu? xi, yi in this region. Değil mi? Diameter is this. Well, maybe I should say the square root of this. Değil mi? Rastgele, you take 2 points arbitrarily and then you look at the distance between them. Peki, o halde bu fonksiyon, so vxy is less than the maximum value of u on the boundary. Pardon, ben bu notasyonu kullandım. On the boundary plus epsilon times d squared. Okay. Bu her epsilon için geçerli. Choose epsilon so that epsilon is positive but less than the following. M0 minus M boundary divided by D squared, where M0 is the value at this point. Bu maksimum nokta her neyse o değer. Biz şunu biliyoruz. Bunu kabul etmiştik. We assume that this is M0. M0 is larger than M boundary, right? We assume that. Bir dakika. Right here, M0 is this value, so it is larger than this one. Hangisi? Ya aslında her nokta için geçerli. Değil mi? Yani çünkü bunun içerideki değeri ama şey yaptım da buna sadece maksimumda bakıyorum. O yüzden mi dedin? Tamam. Bu evet, xy boundary'deyken. Evet. Şimdi epsilon'u böyle seçersem, bu pozitif sayı bölü d kareden daha küçük. O zaman bu durumda vxy epsilon'u böyle seçerdim. D kare ile çarparsam, so when you multiply this with this is epsilon, so epsilon times d squared is less than m0 minus delta, m delta. You add this one, so it will be less than m0 minus m delta plus m delta. Therefore, this is strictly less than m0. Okay? strictly less than m0. So the value of this function on the boundary values is less than m0. Okay. Ama bu fonksiyon da harmonik. Yani buradan ne görmüş olduk? So the maximum of v right, this is equal to v x0 y0. So at some point inside the region v takes this value, but that value is larger than all the values of this function on the boundary. Therefore, the maximum of this function cannot occur at a boundary point. So the maximum of v cannot occur at a boundary point. Peki buradan sonra ne yapacağız? Let v1 y1, which is a point here, so that vx1 y1 is equal to maximum of vxy inside this region. Değil mi? The maximum value of this function cannot occur at a boundary point. Therefore, it's an point in the interior, and let's say it is this point. Aslında bu şuna eşit tabii ki, değil mi? This is equal to maximum on this region. Çünkü burada boundary noktalar da var. Boundary'deki değerler zaten bunlardan küçük. Yani en azından bir tanesinden küçük. So the maximum of this function on this compact region occurs at an interior point. It is not on the boundary. All right. Now we have what? By the second derivative test, right? If you have a maximum point at an interior point of your region, then so by the second derivative test u sub xx x1 y1 should be negative, and u sub yy x1 y1 should be negative. Değil mi? Çünkü if they were positive, then the function would be strictly increasing at this point in that direction. So if this was, let's say, positive, so you are at this point x1 y1, and this point is away from the boundary. Therefore, you have some interval like this, and this implies that your function is strictly increasing. Therefore, at a nearby point, it will take a bigger value, but that's a contradiction. Okay? V sub xx. Okay. But U sub xx and V sub xx, I guess, are basically the same. Yani yok. Hemen hemen. So they are both negative. Okay? They are both negative. And then we do what? Well, therefore, V sub xx plus V sub yy is negative. Since both of them are negative, the sum is negative. Şunu da biliyoruz. O halde V sub xx plus V sub yy, which is just second derivative of v with respect to x is just second derivative of u plus 2 times epsilon, and the same for y derivative. So this is just u sub xx plus u sub yy plus birinden 2 epsilon, öbüründen de 2 epsilon gelecek. So 4 epsilons, and this is negative. Therefore, we see that u sub xx plus u sub yy is less than or equal to minus 4 epsilon, but that is strictly negative. And we know that at an interior point, this is 0. Right? And this is a contradiction. Tamam mı? Okay. Evet. 3 dakikam var değil mi? İyi. Tamam. İyi. Burada bitirelim. Bir dahaki ders bir teorem daha var. Onu da yazacağım. Böylelikle yok. 3 teorem daha varmış ama onlar ispatı yok. Bir tanesinin var. Geri kalanı ya onların da varmış. Neyse tamam. De onlar basit nispeten. Şey olan bu. Okey.